So I guess we've got to fix a natural number, as in GLN. And I need to tell you just a little bit about something that I call OB. OB stands for Oriented Brouwer. So this is a category. I'm working over the complex numbers, so just a C-linear category. So it's got some objects. And the objects in this category, they're just words in that alphabet. So they're just sequences of ups and downs. And then morphisms, well, this is the Oriented Brouwer category. So the morphisms are going to be some Oriented Brouwer diagrams. People probably know this Brouwer algebra story. This is very similar. So if you take so morphisms always in my pictures, they go from bottom to top. So I'm going to put an object on the bottom line of my picture and another object on the top line of my picture. So a sequence of ups and downs at the bottom and a sequence of ups and downs at the top. Then a morphism between those objects is going to be one of these Oriented Brouwer diagrams. Let me try and draw a typical Oriented Brouwer diagram. I don't know, you can have kind of loops and oriented. So everything's got and of course, these strands, they have to be oriented in a sensible way. Can you see that? And so now you see the object at the bottom, it's up, down, down, up. And the object at the top is up, down. And this is a picture which represents a morphism between those objects in the Oriented Brouwer category. A general morphism is just a linear combination of those, because I want a C-linear category. Okay, so in this game, if I have two morphisms, F and G, F composed with G, it's just vertical stacking. You stack the picture of F on top of the picture of G. And people have seen this game many times. When you do this, you might actually create some floating bubbles. And so there's one thing you need to know, which is if you ever have a floating bubble, you replace it. Well, I'm going to tell you about the natural number n. So you replace it with the natural number n. So that's the Oriented Brouwer category, OBN. It's a C-linear category, but it's very good, because it's actually a tensor category. I can take two of these pictures and I can stack them together horizontally like that, and that's the tensor product of morphism F with morphism G. So here it is, it's this strict monoidal category. What's up? Well, they're the same. So I should have said that these pictures, you have to view them up to, these pictures are just pictures of some combinatorial data, which is the bijection between the endpoints that they give you. So there's not really any topology here. These are just sort of pictures of some sort of generalized permutations. And the same goes for bubbles. There isn't really any data in a bubble. It's just how many bubbles you've got. Okay. So I'm trying to show our duality properly, right? So what I've got now is this monoidal category, this Oriented Brouwer category. And maybe I should tell you a little bit more about it. It's actually got a nice universal property. It's the free symmetric monoidal category generated by a dual pair of objects. These objects up and down, they're dual, both left and right in this category. And in a symmetric monoidal category, there's a general notion of categorical dimension of an object. That's just the value of these bubbles. And it's a dual pair of objects of dimension n, because, well, I told you that the bubbles you evaluated at n. And of course, GLN, well, let's look at rep GLN. So there's just finite dimensional rational representations of GLN. I'm over the complex numbers, so it's not maybe good for modular representation theorists, but it's a beautiful monoidal category. It's a symmetric monoidal category. It's generated by the natural representation V, the dual of the natural representation V star. And of course, V and V star both have dimension n. So by the universal property of this diagrammatic monoidal category, there is a strict monoidal functor from Oriented Brouwer to rep GLN, just sending that to the natural representation and down to the dual natural representation. Okay? And show-value duality, well, part of show-value duality is saying that this functor is full. Actually, I can do a little bit better. I'm not going to be able to do a little bit better with the space I left myself. You'll have to remember that. So the thing about this category is it's a semi-simple category. That's not so important for me. What's important for me is that it's a Cherubian category. So it's additive and idempotent split. And so this guy here, well, I should pass to a Cherubian category. So I should pass first to the additive envelope, and then I should take the idempotent completion. So that's called the Cherubi envelope of the oriented Brouwer category. So it's still a monoidal category. It's now additive, and all idempotents have images in this category. And because this was Cherubian, the universal property of passing to the Cherubian envelope means that our monoidal functor extends to a monoidal functor that is still full. And when you have a monoidal category, Cherubian category like this, you can always take some two-sided tensor ideal, additive tensor ideal, and actually there's always there's sort of like a Jacobson radical of this story. There's always a maximal tensor ideal. It's called the ideal of negligible morphisms. And if you factor out the tensor ideal of negligible morphisms, that quotient monoidal category is a semi-simple monoidal category. And show-value duality says that you see, this is semi-simple. So indeed, negligible morphisms go to 0. So our functor passes to a monoidal functor from this quotient. And show-value duality exactly is the statement that these two monoidal categories are monoidally equivalent. Okay, so once we kill these negligible morphisms, it becomes faithful as well, and then it's an equivalence of categories. And in fact, you can do a little bit better. This tensor ideal of negligible morphisms can be generated. It's rather hard from that point of view to say exactly what this is, but it's generated by a very simple element. If you just take the sum over all permutations of n plus 1, sine of g. Okay, so in the oriented Brouwer, you should think about if you only have ups. These sorts of oriented Brouwer diagrams, they're just like permutations. So symmetric groups embed into oriented Brouwer. So if you take these permutations in Sn plus 1 and you just embed them in the oriented Brouwer, this makes sense. It's a particular morphism in this monoidal category. And in fact, that morphism generates the tensor ideal of negligible morphisms. So that's the right way to say show-value duality, in my opinion. Okay. So you can also do the Q analog of this, of course. It's kind of nice. And since when I wrote my abstract, I decided to put the Skein category in here, I'd better do the Q analog. I got bored of it since then, but it's there. So as well as oriented Brouwer, there's the oriented Skein category. Probably I should call it something like the framed Homfly put Skein category. And strangely, this is actually an older object than the oriented Brouwer category. This was introduced by Turayev. I think it was 1987. He called it the Hecker category in those days. And so this has some parameters as well, and I want the parameters are normally called like z and t or something like. The Homfly polynomial is a two-variable link invariant. But I want to specialize z to q minus q inverse and t to q to the n in this game. And I'm going to tell you what this is. Well, it's just like oriented Brouwer. The objects are words in ups and downs. But instead of these rather boring flat pictures with no topology in them, you draw proper tangles. So they're framed oriented tangles. So that means that you have these sort of pictures, but now there's a little bit of crossing information in your pictures. You can have bubbles if you like. You can have caps, and so that's the difference between a framed oriented tangle and these oriented Brouwer diagrams. Oh, and there's some relations here. There's a quadratic. You see over here we just had something like that. was equal to that. Because I said there was no topology in the pictures. This is the crossing squares to the identity. But over here you have this interesting relation which I've written like, so this is the crossing, and the crossing inverse is Q minus Q inverse times the identity. Everyone should recognize that as the quadratic relation in the type A Hecker algebra. I've written it like this because this is the Conway-Skein relation in this form. That's one of the relations. So that tells you. So there's topology now. You see. So this is telling you some of the things you're allowed to do with the topology to get isotopy here. So it's kind of Reidemeister move sort of game. There's this positive twist, and this is what the word framed means. I don't have Reidemeister 1 on the nose. Instead, the positive twist multiplies by t is q to the n. That's this second parameter here. So the positive twist is q to the n. That's this. If you do it, this corresponds to writhe when you're forming link invariant. So this is the framing. Oh, and there was the bubbles, right? So also you have to set the bubble to that scalar, which everybody knows is quantum integer n. Okay? So impose those relations, and this is the Q analog of the oriented Brouwer category. And of course, there's the Q analog of Chauvel duality. You can all guess what it is now. If you take the additive idempotent completion of the oriented Skein category at parameters q minus q inverse q to the n, it's monoid, and you factor out negligible morphisms, but you could generate negligible morphisms by doing the Hecker algebra analog of this. So you'd have the sum of what, minus q to the length of g, and then the Hecker algebra element indexed by the permutation g. So that's this tensor ideal of negligible morphisms. Then this is finite dimensional type 1 representations of quantum GLN, quantized enveloping algebra. So actually, this guy right, so not this guy here, this guy right here. So I put q to the n there, but actually you can take any complex number delta, and you can put q to the power delta in there. And if you take the Cherubi envelope of that, that's called rep underline UQGLN. Or in the Brouwer case, if you take the oriented Brouwer diagram, instead of putting the integer n as the bubble, you put your complex number delta in as the bubble. That's what's called rep underline GL not n delta. These are the Deligne categories for this particular type. And so these are monodal categories, Cherubian. When delta is not an integer, they're semi-simple. Doesn't mean they're boring, they're monodal categories, so they still have tons of interesting structure. But when delta is an integer, they're not semi-simple, and that's when they start having this non-zero ideal of negligible morphisms here, and you can get the usual classical categories of rational representations of GLN or quantum GLN as this quotient, because that's Chauvel duality. It's worth saying that, I said I'm just working over the complex numbers, and Q is generic, so you think this is maybe a semi-simple world, but actually it's not, because when delta is an integer, we have these new interesting Deligne categories that are no longer semi-simple. They have the categories we know and love, these semi-simple monoidal categories, rep GLN over here, as quotients where you factor out the maximal tensor ideal. But these categories themselves are rather beautiful suddenly, and you know, it's sort of just lurking in Chauvel duality. We should have been studying them for more than, well, it's like 1990s, I think, Deligne and Mill introduced these. So it's kind of crazy that these totally cool objects kind of are new. I mean, what's going on? But you know, you can do this in over a field of characteristic P as well. Let me just talk about this case here. You can set this up perfectly well in characteristic P. And you can still write down this oriented Brouwer category and take its Karoubi envelope. And there's still the Chauvel duality functor. So from there to finite dimensional rational representations of the reductive group GLN. And in fact, this statement's still true. No, it's not. You don't get all rational representations. You just get tilting modules. That's a nice monoidal category. It's Karoubian. It's not abelian anymore. It's Karoubian. And you can't say n is this tensor ideal of negligible morphisms anymore, because that would give you a semi-simple quotient. This is not an abelian semi-simple category over here. But this is still the right definition of n. Okay, so that's the right way to say Chauvel duality. It took me 25 years to realize that was the right way to say it. And you can say the same over here with quantum GLN. Let's not do that. I think that's the only thing I'm going to say about positive characteristic. But actually, I think that's quite important. This result. I had a box there for something. I wonder what I was going to put there. You see. Okay, so let's go back to the complex numbers, because despite thinking there wasn't anything more to be said about Chauvel duality over the complex numbers, suddenly we've got this interesting new category. I'll just write rep underline. Pick whichever you like. Pick rep GLN or rep UQGLN if you like. This is somehow quite nice, this world, because you feel like you're doing something like knot theory and you could keep you going a bit longer. There's some topology here, but pick one of them. I don't care which one. They in fact, strangely, they're both equivalent as C-linear categories. Not monoidally equivalent. I mean, this is a symmetric monoidal category. This is merely a ribbon category, but for my purposes, it doesn't matter which one you pick, because I'm only going to be telling you things that have to do with the category structure, not the monoidal structure, for a while. So I'll just write rep underline for one of those Deligne categories. Over the complex numbers. It's not a semi-simple category, because n is a natural number here still. And so it's pretty sensible now. We should ask what does this look like? What do we know about it? Yeah, we should do it in characteristic P as well, but we'll get tilting. But at least first we should do it here. Isn't it crazy that people didn't do this? Because this is Chauvel duality over the complex numbers. So when I wrote my abstract, I thought I'd be telling you about the oriented Skein category, this Turayev category, this rep UQGLN, and I thought I would be telling you about representations of this category. So I thought I might tell you about representations of rep, right? So that's just modules over this C-linear category. If you don't like, what's a module over a C-linear category? It's just a C-linear functor to the category of vector spaces. So it's a totally natural thing to do. So I thought I might tell you about rep. And I think when I wrote my abstract, that was what I was planning to do. But I gave that talk last month in Sydney, so I decided I couldn't give it again. But if I was giving that talk, you might wonder, how do you study modules over this C-linear category? It turns out it's rather, let's maybe just do the oriented Brouwer case where I have these diagrams. You see, there's some very simple thing you can do. In all these diagrammatic categories, you can play this game. You can take one of these oriented Brouwer diagrams, and you can draw it so that all the cups are kind of at the top, and all the cups, no, I got them wrong, cups and caps the wrong way around. It always happens to me, are at the bottom. And all the crossings are sort of in the middle. And if you think about that, this is actually a triangular decomposition. Entirely like in the theory of semi-simple Lie algebras. The cup algebra is like your positive nilpotent, the crossings is like your Cartan, and so on. And so you can do exactly what you do when you learn Fermat modules and highest weight theory. And so it shouldn't really be a surprise that this thing, I'm not going to tell you that story, but just so you can see that it's actually kind of neat, this point of view. It shouldn't be a big surprise that this is actually a highest weight category. Rep. It's a highest weight category. You get standard modules by inducing... what was the Cartan? Of course, it was all oriented. So this crossing part, you could have R up strings and S down strings, and they're kind of tangled, but there's no cups or caps. This crossing part is just Morita equivalent to a direct sum, group algebra of the symmetric group on R strings, tensored group algebra of the symmetric group on S strings, direct sum over all R and S. So this crossing part is kind of two symmetric groups for all R and S. So of course the irreducibles of the Cartan, this crossing part in the triangular decomposition, they're indexed by pairs of partitions. One for the upward strands, one for the downward strands. So you get standard modules in here indexed by bipartitions. And you're away. You've got, it's a highest weight category. It's not quite the usual sort of highest weight category. It's a slight generalization of a highest weight category. I call it an upper finite highest weight category because the poset, the underlying set is these bipartitions that label the simple modules, but you get a partial order structure from looking at composition factors of Fermats. And the poset has a maximal element, but the chains in this poset, there are infinite chains which can go down forever. So that's that's a little bit scary. In fact, the standard modules have infinite length, but the projectives are good. The projectives have finite delta flags because your poset is bounded above. But otherwise, so it's a little bit weird when you start playing with these upper finite highest weight categories, but it's not a big deal. Well, so I could have given that talk. There was just a glimpse of the. If you were in Sydney a month ago, at least one person was. That was that story. So you're good. But I thought what I would do is I would tell you about the Ringel-Dual story. So instead of studying this Cherubian category rep and thinking about the abelian category of modules over rep, which is this upper finite highest weight category, there's actually another category around which is called rep ab. It's the abelian envelope. And it was constructed a couple of years ago by Entova, Hinich, and Serganova, and I'm not going to tell you their story either. But this is an abelian monoidal category. In fact, there's a monoidal functor from this guy to this guy, which has the obvious universal property, making this the abelian envelope. But constructing it was highly non-trivial. But morally, it's the Ringel-Dual. I'll just put it in quotes, because I don't want to say exactly what I mean. So this was our Cherubian Deligne category. This is the abelian Deligne category. Morally, they're Ringel-Dual objects. So in particular, the poset for the Ringel-Dual, Ringel duality switches the order, right? So the poset will be bounded below. And indeed, whatever this category, this rep ab is, it's a lower finite highest weight category. Now, we're much more familiar with them because, for example, rational representations of a reductive group in characteristic P is a lower finite highest weight category. You have these infinite chains. So your standards have finite length, but it's things like injectives that can be a problem, right? Your injectives have infinite nabla flags. That's this world. But tiltings are good. Tilting's still finite dimensional. Well, this is like that. It's not actually rational representations of a reductive group, but it's got all that flavor. It's exactly tilting modules. That's exactly the statement that, well, this is Ringel-Dual of this. If you take the full subcategory generated by tilting modules in here, you exactly get this. So, it's easy to say that this is the Ringel-Dual of this. It's harder to say this is the Ringel-Dual of that. One should say it, but I'm not going to tell you what it means. Okay, so this is kind of nice, a little generalization of upper and lower finite highest weight categories, and this nice generalization of Ringel duality. It's quite nice. Really, it's a sort of doing what Steve Donkin did in papers 1, 2, 3, 4, 5, where he would always take a finite ideal in the post set and look at these finite dimensional, and it's just doing it all at once, putting it all together, and you get these upper finite highest weight categories. Was it 5 or was it 6? Parts 1, 2, 6. Okay, so let's keep going. So I'm sort of in not giving this talk and deciding to give this talk. What I'm really doing is I'm skipping to the end and we're going backwards towards the middle again. So there's all that stuff in the middle that I've not told you about. So maybe it won't make any sense now, but so maybe I'll write down a theorem and maybe it'll help. Let B be any block. Well, let me just stick with rep. So as I said, I'm really trying to tell you about the Ringel dual, but let me at least tell you what rep was, right? This Deline category. Pick any block of that category. Then the theorem says that B is Ringel dual and certainly that it's going to just be one category here. So particularly it'll mean that all blocks are equivalent. Doesn't matter which block you pick, I'm going to get the same thing over here. And the category I'm going to put here is going to be, I'll just write it, perv gra infinity. And I'll try to tell you what I mean by perverse sheaves on the infinite Grassmannian in this setting. But it's not scary. This is something very easy. But I love this theorem because it's kind of the hint that I mean, this is the closest I've ever managed to get this thing to something geometric. And this is a very explicit, simple geometric object. And I'm going to explain the theorem, what it says. I'm not expecting anyone knows what it says yet. I'm going to try and give you kind of some of the clues as to how I might be able to prove this theorem when I don't really know what perverse sheaves on the infinite Grassmannian is. Because the proof will be just something purely algebraic. But it's such a suggestive statement that there's got to be something going on that should be a better. So let me tell you what the theorem's saying. Okay, so let's try and get there. So maybe we should start with an ordinary Grassmannian, Gr sub R. So this is R-dimensional subspaces in C2R. That's what I mean by Gr sub R. So that's a beautiful complex variety. It's got a nice stratification, the Schubert stratification, and you can just look at ordinary perverse sheaves on this beautiful projective variety. So this is one of the simple examples that there is in the world. Everyone should know this example. So this is some abelian category. In fact, it's the highest weight category. And let me just at least give you a little bit of the combinatorics of this category. Let me tell you what the weight poset is. I'll denote it lambda sub R. So this is the Grassmannian of R-dimensional subspaces in C2R. So of course we should be looking at minimal length coset representatives of SR cross SR in S2R with respect to the Bruhat order. And I'm not going to think about permutations and cosets or anything. I just want to this is something totally easy. These are kind of shuffles. So let me see, if I write minus R through to minus 1, 1 through R, you can take that sequence and you can shuffle that sequence preserving the plus and the minus orders. So you're not allowed to mess up the orders of the negative guys or the orders of the positive guys, but you can shuffle the positive and negative guys into each other, right? That's exactly these minimal length coset representatives. So this is our weight coset with respect to the Bruhat order. So in particular, this guy here, this is the identity shuffle that corresponds to the identity element. This is minimal. So, okay, so perverse sheaves on this Grassmannian, this is the set that indexes its simple modules. And you can do a very obvious thing. If you have some shuffle, not just the identity, any shuffle, you can just tack on that at the beginning and that at the end, and you get an r+1 shuffle. This is this embedding of lambda r into lambda r plus 1. In fact, this guy here, this is a poset map. This guy here is an ideal in this poset, so a lower set in that poset. And then, of course, lambda infinity is going to be just the union of all of those ideals. So we're going to be looking at kind of finite-ary shuffles. So shuffles of this infinite sequence where you're only allowed to move finitely many things and you can't mess up the negative or the positive orders. Okay, so that's our poset. And this identity one, so this is exactly this lower finite poset. That's the identity at the bottom. Okay, so whenever you have an ideal in a highest weight category, maybe I put perv r plus 1 there. You can take the highest weight category and you can look at the Serre subcategory consisting of the simples in that ideal. So that turns out, if you do it for Grassmannian r plus 1, you get exactly the perverse sheaves on Grassmannian r sitting inside it as a Serre subcategory, corresponding to that ideal. And then all the perv infinity is, it's just kind of the maybe we'll write the limit, direct limit over all r of those guys. So I mean, you can think about infinity as being some invariety, and this is exactly what perverse sheaves on that invariety means. And Peter will tell me what the appropriate closed embedding is of Grassmannian r and Grassmannian r plus 1. You can all work that. Okay, so this is okay. It's still a little bit frightening, but at least I've got some combinatorics on the board. So where's the theorem? Here we are. So we have this kind of union of these ordinary finite highest weight categories where we've taken a union of ideals. So this is one of these very nice lower finite highest weight categories. The tilting modules are good here. So what you can do is you can take the tilting modules, T of lambda, indexed by all of the weights in the poset, lambda infinity. And you can, I want to take their, there's infinitely many of them still, so I should be a little bit careful. I should take the direct sum of the Homs, because I like that sort of, that's an algebra. That's the Ringel dual of perv infinity. It's exactly that algebra. Okay, so the right way to say it is it's the full subcategory generated by the tilting modules. But let's just take that direct sum of Homs, and that is, it's not a unital algebra. It's kind of an idempotented algebra. It's locally unital. And I'm saying that is Morita equivalent to this finite dimensional C-linear category that we had. That's the theorem. Okay? So I want to try and explain why this is such a cool example, and this is not anything. This is my favorite example of this whole. Okay, no, the Templey category is my favorite example. This is my second favorite example of this whole story of finite dimensional algebras and perverse sheaves on flag varieties and category O and this whole big story. This is my favorite example because you can calculate it by hand, see everything, and there's so much structure. So let me see. That's not bad. So let me tell you how to construct this abelian category here. Let me tell you how to construct it absolutely concretely. And of course, this is actually how I prove this theorem. I just get my hands on this and calculate this explicitly. And so it's very important in my algebraic proof of this geometric-looking theorem that this is something I can just pick up. So this is it's been a while since I gave the talk on this subject, but as I say, I think it's just a very lovely example. It's been a good 5 years since I gave this talk about Kovanov's arc algebra. There's these algebras called H sub r. Kovanov arc algebras indexed by this natural number r. I'm going to maybe cheat you a little bit. I'm not quite going to tell you the full definition, but let me give you some examples. Let's do H sub 1. These are just finite dimensional algebras. They're basic algebras. They're positively graded as well. They're very simple algebras to get your hands on. But the way they're defined is you write down an explicit basis given by some diagrams, and you say an explicit combinatorial rule to multiply the basis. So this is a sort of totally hands-on, down-to-earth object. So H1, well, it's very boring, H1. It's two-dimensional algebra. And I'm just doing it by example so you see what the basis looks like. It's two-dimensional, and the basis is these two diagrams. It's the counterclockwise circle and the clockwise circle. Okay? And it's a very boring algebra. It's that algebra. It's not completely a very boring algebra because it's the cohomology of CP1. And so it's got a Frobenius algebra structure. So there's a little bit going, but it's still pretty boring algebra. This is 1 in this algebra, and the clockwise guy is x. And there's a combinatorial. So I'm drawing these diagrams this way because I'm just going to do multiplication a times b just in the natural way, putting a next to b. So there's no monoidal structure here, so there's no reason for me to twist you around and stack vertically. So I'm just going to do it this way. Okay. Good. Okay, so I'm just trying to teach you very quickly what these algebras are. So I'm just going to show you H2, and then I'm going to just kind of mutter some words, and that'll be, I'll have done that job maybe. So H2, here's the basis. So some diagrams, right? So there's always an axis in the middle, and then on the left of the axis there's always R is 2 here, of these left arcs. And on the right there's going to be 2 of these left arcs. So here there was just one left arc, one right arc. And then down the axis, there's some arrows which give you orientation on the circles that you form by gluing these left arcs and right arcs together. So what can we do here? We can, you see those are 2 left arcs and 2 right. The arcs are not allowed to cross. So it's sort of Catalanish combinatorics for the left arcs and the right arcs. So there's, or you could put your arcs like little arcs, or you could have little arcs and nested arcs, or you could have nested arcs and little arcs. Right? So those are the only ways of putting 2 arcs on the left and 2 arcs on the right, so there are no crossings. And then you've got to orient the picture. That's this data. So this outer circle can be anti-clockwise or clockwise. The inner circle anti-clockwise. So actually there's 4 choices here, and so each orientation will give you a sequence of arrows down that axis, right? And well, actually, I've just drawn the identity shuffle, but the leftward pointing arrows and the rightward pointing arrows in general will be shuffled together. Oh, the labels down the middle are these shuffles lambda r that we had before in disguise, right? So this is like -2, -1, 1, 2, and so this yeah. So maybe I write some words on the board randomly. This basis that I'm giving you is a cellular basis for this finite dimensional algebra. The poset is this is this poset lambda r that we had from our shuffles, and they appear just down the middle axis of this, so you sort of maybe see the ingredients of a cellular algebra if that's your game. So there's 4 such basis vectors. There's 4 such basis vectors. There's 2 such because there's only 2 ways to orient. There's only 1 circle and 2 such. So what is it? 4, 8. That's 12-dimensional, which is a totally meaningless number. And then, as I said, there's a combinatorial rule to multiply these guys, which I'm not going to show you. But it's a beautiful rule. It was discovered by Kavanagh, and it's kind of underlies his theory of categorifying the Kaufman bracket for tangles. His categorified version, the Kaufman bracket of a tangle, is some complex of bimodules over these algebras. So it's totally wonderful. But very quickly, the multiplication is gotten by. So if I had to multiply these 2 guys, you have to sort of you have to smooth out these 2 middle bits of the picture so that you can sort of squish them together. And you do that by doing some surgery, by kind of stitching open and re-gluing these right arc, left arc pairs. And then there's some combinatorial rules for how you reorient when you do this. And the combinatorial rules come from the TQFT associated to this Frobenius algebra. So it's kind of a cool, but I'm not filling in that picture. All you need to know is that it's a cellular algebra, and lambda r is the weight per set. Totally explicit way to multiply. And HR in general is just the same. It's just you have R left arcs and R right arcs on here, and there will be this algebra. Okay, very good. Did that. Okay, good there. Very good. So, I'm just going to do one little tiny thing, and you know, I'm doing the easiest example, so it's kind of nice that it's possible. I'm gonna stick with H2 here, and I'm going to define I11 inside this 12-dimensional algebra. I'm going to define it to be spanned by all the basis vectors which are not. What I want is I want to keep those guys. So, which don't have a left and a right at the top and the bottom. This you'll recognize as I'm throwing out everything that wasn't in this ideal in my poset here. So everything that's not in here, this is a 2-sided ideal of H2. So the span of so maybe we should list all the diagrams that are good, all the basis vectors that I'm killing. And my ideal is all the other basis vectors that I'm not about to write down. Okay, so let's do that just here. So what base? So I've got to have a left at the top and a right at the bottom. So otherwise it's in my ideal, and I'm going to factor out that ideal, and it's gone. Okay, so I guess there's 2 such, because the middle circle I can still make it anti-clockwise or clockwise. This type, I want to have a left there and a right there. Well, there's only one possibility, because everything's got to be oriented in a sensible way. This guy here, I want a left there and a right there. Well, you know, there's only one possibility. And this guy. And what's the dimension of that algebra, Geordie? Very good. Okay. So. So my ideal is everything which is not left-right like that. Okay, and I'm gonna set K sub 1 to be H sub 2 factored out by this ideal. So this quotient algebra, these 5 guys give a basis for this quotient algebra. So this is the category of perverse sheaves on the Grassmannian GRO 1. In our notation. I mean, I know this better because it's the principal block of category O for the Lie algebra SL2, and that's why I think many people know that number 5. I was just really checking that Julie wasn't asleep up there. Oh, you were very lucky. But you just had to know that you had to say 5 at some point, right? Okay. So this is a very little example, but it's enough. So more generally, you take R less than or equal to S, and you look at the ideal in HR plus S. This is an ideal in HR. We just did I11 in H2 just then, where you kill all the diagrams where, let me see, what you're trying to do is get S guys good. And then, of course, in the middle here, there can be anything you like, and there's 2R such vertices in there. Does that make sense? It's a little cryptic, but so right. So that's an ideal in this post set. So this is a cell ideal in this cellular algebra, and I'm going to define K sub R to be the quotient algebra. And you'll notice there's a little choice of S. There's lots of S's that give the same KR, so that's a little lemma that it doesn't matter which S you pick as long as it's very equal to R. And now we can get to the punchline very quickly. This was a while ago. The category of perverse sheaves on the Grassmannian graph R is the same as modules over the algebra KR. So in fact, this is the basic algebra that kind of realizes this abelian category. So hopefully that makes this category of perverse sheaves on the Grassmannian graph not that scary. I mean, this is something totally concrete. It's just a great example. Okay, so now I have a couple of minutes. So we're going to take limits. I've got all these Kavanagh-Fark algebras, H1, H2, and they all embed into each other. The maps, kind of, if you have some diagram with 2R vertices in there, here's how you embed it into the next Kavanagh-Fark algebra. You put a great big clockwise circle around. And that's an algebra embedding. It's not unital, so it's a little weird. We're in this locally unital world. And then you form H infinity, which is just the direct limit of all of these things taken in this category of idempotented algebras. You should work in the category of categories, but it's a bit crap to do that. And corresponding to this, these algebras K, which are our perverse sheaves on Grassmannians, these are all quotient algebras, right? I mean, these guys here, they're all quotients of H6. This was why it was important that I had this freedom of this S here. These guys, and this, we're killing a little bit more each time. So this is this inverse system of these algebras K. So each of these guys are quotients. So that's where these maps come from. And really, this H infinity, which is this direct limit of these, really a better way to say it is it's the inverse limit of this inverse system here. Because, well, modules over a quotient algebra is a Serre subcategory of modules over the whole algebra. And this is this perverse sheaves on Grass infinity being this direct limit of perverse sheaves on all the Grass R's. This is what these KRs realized as quotients. So you see that this category is very elementary. Okay, and then I've just got a couple more lines. So long ago, well, it felt like long ago. With Katerina. Finite dimensional modules. This is why this world is nicer. You don't have to worry about anything. These lower finite highest weight categories are nice. You won't have injectives or projectives. Oh, well, you'll have it. You won't have projectives, but they'll be the wrong injectives. Okay. So long ago, what we did is we actually. It's so long ago I might have remembered this wrong, but we did something like this. we actually constructed a totally different bunch of maps from these algebras K that went in the other direction here. And I'm not going to write them down, but we defined an algebra we called K infinity by taking a direct limit of those KRs. And so what's let me kind of come to this new way of saying things, which I like much better, is that last year we proved that K infinity and H infinity are Ringel duals. This is nice. This modules over this is this lower finite highest weight category. This is not so nice. This is one of these, you have to make sense of, you have to start allowing infinite dimensional modules here and be a little bit careful. And it gives you one of these upper finite highest weight categories. And so what I recently proved was that K infinity, this is my sign for Morita equivalent, is Morita equivalent to B. You remember B? It was a block of rep that we fixed. It doesn't matter which, but they're all Morita equivalent, and they're all Morita equivalent to K infinity. And so that's the theorem I told you earlier, that these blocks, they're all Ringel duals to this perverse sheaves on great infinity. And so, I mean, there's a little bit of magic in there that I'm not telling you about, which is pretty terrible, actually. And it's really why one wants to have a nice new proof now that's geometric in nature, because one doesn't really want to have to play all the games with two-representation theory of Kac-Moody two categories that go into that uniqueness result. That anyway, let me stop. Yes.
It seems like at some point in this equivalence you're inverting a lot of numbers, which suggests that maybe there's not a really good reason for this equivalence.
Yeah, I mean, part of what I've done here is rep was monoidal. What I'm doing is getting a tiny little shadow of rep. I'm seeing what the basic algebra Morita equivalent to one of the blocks of rep is. So I've totally destroyed the actual nice structure, which is this monoidal structure. So my hope is that there's some actually geometric monoidal category that's much bigger than this perverse sheaves on Grassmannians, but which for some reason has blocks that look like perverse sheaves on great infinity. But it should have the monoidal structure there as well, and that's really what my... Yeah, I should have said Braden in there. So there's two proofs of this theorem. And there's a proof where Tom Braden gave a presentation of this category. So he essentially computed generators and relations for the basic algebra that's Morita equivalent to this category. But in a for me a rather awkward form. So it's a lot of work to get from Braden's presentation for this category to this arc algebra description. And it was worked out a couple of years later by Katerina Stropel. So I should have said that history, but I'm happy I had the chance to. And then I came along and I said, well, okay, I don't want to do it that way. We should be able to get straight to the arc algebra. And now with all the modern categorification techniques, it's totally painless to go straight to the arc algebra. I mean, going from Braden's presentation to the arc algebra presentation is Katerina's paper, and even that's it's some sort of logarithm, taking logarithms of Braden's relations. It's kind of a scary process. It's not. Yeah. Right now, that's the only way I know it. I mean, it's kind of a cool fact. It happens for other Deligne categories. There's this Deligne category rep ST. That also has this phenomenon, and that's used by Rostrick, for example. So somehow these Deligne categories are magic. They're not semi-simple, they're monoidal, but over the complex numbers, they're all tractable, and it leads to this whole wealth of beautiful algebraic theorems that you kind of dream of doing things like that in characteristic P.
For rep ST, is there something geometric?
No, I mean, there's really just this paper by Combs and Ostrick where they construct the abelian envelope of rep ST. And they have this nice bunch of analogies to Tapley-Leib, essentially, to representations of quantum SL2 and the Linde category. But there's no, it's just algebra. You have these things that are, they're simple enough that you can do algebra, but there's more beauty here that we don't quite understand yet.
So at the start you said that this is shown optionality, this way of breaking it. So now you've understood this, would you say that to some extent the papers you started with Katerina, you finished the project that you were on, or is there more to do?
Who knows? There's always more to do. I mean, I'm kind of hoping I don't have to write any more papers with these art pictures, but it looks like I'm going to have to write one more.